Hi viewers, welcome to my class on mechanics of materials. In this class, I'll explain stress strain diagram and introduce the concept of factor of safety. A stress strain curve for a material gives the relationship between stress and strain. To obtain the stress strain diagram, we gradually apply load on a specimen and measure the deformation produced. So by conducting the test on a specimen and plotting the stress strain curve, we can find out the yield strength, ultimate strength, fracture strength, and even Young's modulus of the material, and it helps to know the suitability of a material for a specific purpose. A universal testing machine or UTM is used to conduct tensile or compressive test on a specimen to find out the elastic properties. This figure shows the tensile test specimen, and the ends of the specimen are having larger diameter compared to the center region where you make the measurements, and these 2 points, mark points, the distance between those 2 points is known as gauge length, and the deformation is measured in this gauge length, and the forces are applied on the ends through the grip where the specimen will be fixed on the jaws of the UTM, and so both the ends will be fixed on the jaws of the UTM and tensile forces will be applied. Deformation in this marked portion, that is gauge length, will be measured, and also you can measure the force applied through this dial. So the deformation will be measured through the extensometer fixed on the UTM. So you can measure the deformation produced in the gauge length, and also you can note down the force applied to the specimen, tensile force applied to the specimen. So once you know the force, you can find out the stress induced by using force by area of cross section of this test portion, that is between these 2 points we have uniform area of cross section. So the force applied, the tensile force applied at a specific point divided by area of cross section will give the stress, and at that point what is the extension produced you can measure, and that extension divided by the initial length, gauge length, that is initial length, will give the corresponding strain. So you get a value of stress and strain. As the load increases, you can measure the stress and corresponding strain. So you will get a number of values of stress and strain, and using this you can plot the stress strain curve. Now this last figure shows the specimen, and finally before breaking there will be a neck formation. Somewhere in the gauge length portion there will be a neck formation, and the area of cross section considerably decreases. So this is before breaking, there will be a neck formation and the cross section area decreases, and finally the specimen breaks. So tensile test is conducted till the specimen breaks into two pieces. This diagram shows the typical plot of a stress strain diagram for a mild steel. So corresponding to each values of stress and strain, we plot points, and finally you get the stress strain curve. So you take a number of readings from the experiment and plot the stress and corresponding strain. So corresponding to a stress you get a strain and you get a point here. Similarly another value of stress and strain, you will get another point. So you will get a number of points, and plotting this you will get the stress strain curve, and the solid line represents the nominal stress strain curve. Nominal stress strain curve means stress is calculated based on the initial area of the specimen. So initial area means we are not considering the neck formation and reduction in area. Without considering the reduction in area, if you are taking the initial area, that is original area, then you can calculate the stress. Load divided by this area will give the stress. but when the neck is formed, there will be a reduction in area. The actual stress will be more. Load divided by area is less, so stress is more. So without considering this reduction in area, if you are using the initial area, that is called nominal stress. Okay. Whereas if you consider the reduction in area, that will give the true stress. So this solid line represents the nominal stress strain curve without considering the reduction in area. So usually we plot nominal stress strain curve. We will not measure the reduced area, or reduction in area will not be taken, and plot the stress strain curve. It's difficult to measure the instantaneous area after the neck forms. So usual plot is this nominal stress strain curve, or if you plot it based on the true stress, the nature of curve will be as shown by the dotted line. Now I have marked number of points here. So A is a proportional limit and B is the elastic limit. A and B are very close points, and most of the materials there is no distinction between proportional limit and elastic limit, and they are very close point, and if they are distinct, elastic limit is going to be slightly above the proportional limit, and they are also used interchangeably. So Hooke's law is valid up to this proportional limit or elastic limit. Proportional limit means the stress is directly proportional to strain, or the portion of the stress strain curve is straight, linear. So B is the elastic limit beyond which the material cannot regain its original shape. So if elastic limit is exceeded, on removal of load, the material cannot regain its original shape. And C is the upper yield point. Upper yield point and lower yield point are exhibited by certain materials like mild steel, and this upper yield point is where the material starts yielding and plastic deformation takes place, and D is the lower yield point, and that is a lowest stress at which the material continues to deform plastically. Lowest stress encountered at which the material still deforms plastically, so that's a lower yield point. And E is the ultimate stress or ultimate load point, where maximum stress is encountered during the tensile test. And F, the material breaks or fractures, and it is the fracture point, and corresponding value gives the fracture stress. So corresponding to this A, B, C, D, E, F, you can find out the stresses. So stress at elastic limit, stress at yield point. Okay, it's usually upper yield point will be taken. So stress at yield point, ultimate stress, and you get the fracture stress. Now true stress, the plot goes like this, and fracture stress is always greater than the fracture stress given by the nominal stress strain curve, because true stress strain curve, the reduced area is taken, and the actual stress at the point of breaking is always greater than that is a maximum stress encountered. So actual stress at the time of breaking is always maximum. Now this gives a typical plot for stress strain curve for a brittle material and a ductile material. Mild steel is also ductile material, but mild steel shows typical characteristics of upper and lower yield point. Yeah. This is particularly for mild steel I have plotted. Mild steel is also ductile material, but generally you can say that the brittle material will have no well defined yield point, and suddenly the material breaks, and the stress at there is no yielding, no neck formation, so suddenly the material breaks, so the stress strain curve always goes up. Okay, there is no dropping. So whereas in ductile materials it drops because of this is a nominal stress strain curve, and the stress at time of fracture is less than the ultimate stress. So it is not the peak stress at which the material breaks, because this is based on the initial area, not based on the actual instantaneous area of the specimen. Now coming to factor of safety, it is defined as the ratio of yield stress to working stress for ductile materials. Now the point C indicates the yield point. If you are loading the material beyond point C, there will be a permanent deformation in the material. So it is not advisable to load beyond C or even up to C. So we need to limit the stress within the yield stress. So beyond C, if you load, the material fails. So you want to limit the stress within this yield stress. So if a yield stress of a material is 200 megapascal, we cannot load up to 200 megapascal. 200 megapascal, if you load, the material starts yielding. Okay, so that is a yield point. So we have to limit the stress somewhere here. Okay, so not even to the nearer to the yield point. So you want to limit the stress to somewhere here. So for that, say let us limit the stress to 100 megapascal when material is put into service. You are limiting the stress in the material during its service to 100 megapascal, even though the yield stress of the material is 200 megapascal. So this 100 megapascal is known as design stress or working stress. You are limiting the stress to 100 megapascal and the material yield stress is 200 megapascal. So this yield stress divided by this working stress is known as factor of safety. So yield stress divided by working stress. So 200 divided by 100, which gives a factor of safety 2. So you are reducing the stress by 2 times and reducing the risk of failure. So even though yield stress is 200, we are limiting the actual working stress to 100 megapascal or design stress to 100 megapascal, so that when material is loaded with the maximum load, the stress is coming to only 100 megapascal and you are safe. So if you are going for a higher factor of safety in the example which I given, suppose we take the factor of safety 4, yield stress is 200 in the example given. So 200 divided by factor of safety, yield stress by factor of safety will give the working stress. So 200 is yield stress divided by factor of safety 4. 200 by 4 will get the working stress as 50. So you are limiting the working stress or design stress to 50 megapascal during the service of that particular component. So accidental overloading sometimes increase the stress beyond the design stress, but still the material will be safe because you are using a factor of safety. So this is a definition of factor of safety for a ductile materials. Ductile materials, it's defined as yield stress by working stress. But for brittle materials, which does not have a well defined yield point, it is defined based on the ultimate stress. So factor of safety is defined as ultimate stress divided by working stress. So in that case, you need to have a higher factor of safety because it's based on the yield stress is always less than the ultimate stress. When the factor of safety is defined based on the ultimate stress, you need to use a higher factor of safety. So for brittle materials like this, based on this stress, ultimate stress, you define the factor of safety. You want to limit the stress to somewhere here. So ultimate stress divided by the working stress, that will give the factor of safety. So if ultimate stress is 300 megapascal and if you are using a factor of safety of 6, 300 by 6, you will get the working stress as 50 megapascal. That's all for today. Thank you for watching.